Our third type of UML diagram is the sequence diagram. These describe the sequence of method calls or system accesses in response to a user story. The goal of the sequence diagram is to document how the system will be built, which classes will interact, and in what way. This is the first diagram that actually documents the order of actions within the system and which entities communicate with what other entities. Sequence diagrams can describe high-level interactions of subsystems or low-level interactions of classes. They are best suited for thinking through complex logic or documenting the logic behind methods or services. We generally create one or more sequence diagrams to handle each use case. Like other forms of UML diagrams, there are relatively loose standards, but the basic elements of a sequence diagram include a list of agents or subsystems across the x-axis, aligned to the top with vertical dashed lines extending down parallel to the y-axis, representing the lifetime of the entity. The y-axis itself represents time going down. Horizontal arrows indicate one entity accessing or communicating with another entity. In this generic example, the actor class creates an instance of some class, which in turn creates an instance of subsystem. The vertical rectangles represent the time that processing is being performed, or the entity is waiting for a return value from another entity. The large ref box represents an interaction use, indicating that the following code is reusable in some way, or it can also reference another sequence diagram. Finally, we see an asynchronous method call. This indicates that the actor class does not need to wait for the response from another class. Here we see a simple interaction where the cashier gets a customer in their line, and then processes the customer. The clock notifies the cashier that it is time for them to get to work. The cashier then gets the first customer from their line and processes the customer, then saves the timing statistics so that the average processing time can be saved over time. Notice that the cashier waits for a first customer to be returned, but does not wait for a response from the statistics object. In this example, the clock notifies the customer pool that it is time to generate a new customer. The customer pool creates a new customer and then gets the random number that represents the arrival time for the next customer. The customer pool then reports back to the clock where the time is registered as an alarm. Here, the supermarket checks the cashier collection to see if it needs to add or remove any cashiers. If the shortest line is greater than 5 customers, a cashier is added. If the idle time of a cashier is greater than 4 minutes, it removes a cashier. Here, we extend an earlier sequence diagram to indicate how statistics are maintained over multiple customers. The cashier finishes processing the customer, and then the customer determines their wait time and tells the cashier. The cashier then accumulates that time in the statistics object. The cashier also accumulates the length of their line multiplied by the time the line has been that long through the cashier queue. The cashier then updates their length of time with the statistics object. Finally, the cashier removes the customer completely from their line, and then the cashier queue resets its timer. Here we see a model of reuse that we can only detect through a sequence diagram. Here, the clock wakes up an entity, and that entity fires off an action. After each action is fired, the entity then responds to the clock by registering a new timer. This indicates an opportunity for reusable design and a set of methods that easily allow any of these entities to complete this action easily, such that the clock does not need to know what entity it is waking up.